Alright, so today I'm going to be presenting an important paper with the title MMD Graph Kernel, Effective Metric Learning for Graphs via Maximum Mean Discrepancy. This I clear paper in 2024. This paper focuses on graph metric learning. First, we present a class of maximum mean discrepancy based graph kernels called MMDGK. These kernels are computed by applying MMD to the node representation of two graphs with message passing propagation. Secondly, we provide a class of deep MMD GKs that are able to learn graph kernels and implicit graph features adaptively in an unsupervised manner. Thirdly, we propose a class of supervised deep MMD GKs that are able to utilize label information of graphs and hence yield more discriminative metrics. You see the architecture of MMD graph kernel in vanilla and deep version, where the model is graph convolutional networks. The main steps consist of embedding aggregation, kernel mapping, distance to similarity, and for GCN, updating parameters. MMDGK can be evaluated in downstream tasks such as graph clustering and graph classification. An attributed label graph is a graph with n vertices endowed with an attribute function that assigns d-dimensional real-valued vectors to vertices of the graph with a label function that assigns label to vertices of a graph from a discrete set of labels. Then they define L-level node features. Given an attributed label graph, the L-level feature of a node aggregates all features in its L-order neighbors, including edges, node attributes, and labels. This is the definition of maximum mean discrepancy, which is very important in machine learning. Now, we have two distributions, P and Q. And also we have a kernel K. Now we can see the distance between two distributions based on these kernel. And mu P and mu Q represent mean of their distributions and in their reproducing kernel Hilbert space. So XX prime, YY prime, they're just sampling. They're being sampled from P and Q respectively. Another definition that we need is generalization of MMD. Given a family of positive definite kernels, the generalized MMD is the supremum of the distances. And then they define the estimated. The estimated, because we have here the expectation, now they replace it with this approximation of expectation for each of the terms here. Another definition that they need is consider a collection of attributed label graph. Each graph is assigned a label through a surjective function. The labels represent distinct distributions of node attributes and labels. So for a given label C, the graph distribution is defined with respect to node attributes X, label Y, and their combined feature at a specific level L. The L-level node feature with the same label follow specific distributions. Then they define MMD between two graphs by supremum of the distance between their means induced by a graph G1 and G2. So what are the key steps on the very normal MMD GK? Not a deep version of that, just a vanilla version. The key steps is that the model employs an embedding aggregation mechanism to iteratively update these node representation till L levels. Specifically, at each level L, node representations are updated according to the normalized adjacency matrix. Subsequently, the model utilizes MMD to quantify the dissimilarity between two sets of node representations with a size of N1 and with a size of N2. So this D hat is a distance metric that satisfies the metric space axioms that it should satisfy this triangle inequality. By default, a Gaussian kernel parameterized by a bandwidth h is employed. So this h in the denominator is just the bandwidth of that. So we use this Gaussian kernel here in order to obtain graph kernel S, which is similarity between G1 and G2. So e to that distance that we have defined, now it becomes a kernel. Then they prove this inequality. It is upper bounded by these terms. Now the algorithm just returns S and the W's. First we initialize the W's, and then we embed propagation with parameters. Then we calculate distance to similarity. Then using the backpropagation from loss, because you have the loss, then you can update the parameters. And here the output is estimated similarity between G1 and G2. That we have embedding propagation, kernel mapping, distance to similarity. And this is just the deep version. I showed you the shallow version, the vanilla version. Now this is the deep version. So they use supervised contrastive loss. When all training graphs are unlabeled, we can still learn deep MMDGK using two loss functions. The first loss function is, as I said, unsupervised contrastive loss, because we have negative samples. And the second loss is KL divergence. And these are soft cluster frequencies. The model learns to adjust its embedding to better reflect the natural cluster property of the data. And then theoretical analysis. Then they talk about computational complexity. You see the computational complexity for graphlet is n to the k, order of n to the k, but for them is much reduced. It's order of n2d and then nd. So they did experiments on mutog proteins for graph classification. They compared, for example, shortest pass or graphlet kernel to deep version of that, both supervised and unsupervised.